Okay, we are going to start on chapter 3. Uh, so chapter 3 starts to cover matter and energy. So we're going to talk through these topics. Um, this chapter starts with a discussion about classification. When we're talking about classification, we're talking about putting different types of matter into certain groups where they have things in common with other substances. This flow chart is a good representation of the breakdown that we want to be able to do with each of the substances that we're looking at. Okay, and we'll talk through this step by step, but a good goal for yourself for this section is to be able to recreate this flow chart for yourself um, by asking a series of questions that helps you determine which pathway the substance that you're working with would take in this flow chart. Okay. So first of all, we're classifying matter. And as a reminder, matter is going to be anything that has mass and occupies space. Okay. So just about, everything that we interact with, that all contains matter. And when we're going through this classification, um, we're going to classify the matter into different categories, right? And the two main categories that we're going to work within are going to be the category of pure substances versus mixtures. Right? That's the first step in categorization. Pure substances are going to be anything that has a fixed or definite composition. So its composition is never going to change. Its proportion of the components that make up that substance will not change from sample to sample. With mixtures, you're going to have two or more things that are originally different substances that are combined together. But the combination of those substances is only going to be a physical, right? So you're taking two things and you're putting them in a space together, but they're still going to be their own individual substances that are just, they happen to be in a container together. No chemical bonds are going to form. They're not going to combine chemically. Okay. Pure substances have um, their own categories that we can continue to break them down into. And those categories are going to depend on whether the substance you're working with has only one type of atom that makes it up. If that's true, if there's only one type of atom, the substance that you're looking at is going to be considered an element. A compound, on the other hand, is going to be composed of two or more elements. All right. So you're going to have at least two elements that make up a compound. And these elements are going to combine in the same proportion in every sample. Okay. The proportion that they combine in will never change. We'll look at some examples of this in a second. We'll just go on with these definitions first. So when you have elements, these are going to be pure substances that contain only one type of material, right? So you start out with matter, everything is matter. And then when you decide something is a pure substance, meaning its composition never changes from sample to sample, then you can decide whether you're looking at an element or a compound. And if it's an element, that means there's only one type of atom. So these are examples of elements. If you have more than one type of element, then you're going to have a compound. So these are examples of compounds. Things like hydrogen peroxide, things like table salt, which is just sodium chloride, table sugar, C12H22O11, water, H2O. These chemical formulas, they never change for these samples. When you have hydrogen peroxide, you always have two hydrogens for every two oxygens. That never changes. Okay. This is just giving us a look at what the makeup of table salt is. It's composed of sodium, metal, and chlorine gas that combines to form the sodium chloride that we see in our salt shakers, in our containers of salt that we get from the store. And then we have mixtures. So mixtures are on the other side of that flow chart. And with mixtures, we're going to be looking at two or more substances that are mixed together, but they're not going to be combined chemically. Okay, they're not forming any kind of chemical bonds. The substances can be mixed together in different proportions depending on how they're made. And the substances are also able to be separated by physical methods. For example, a physical method would be if you use like filtration to separate a solid liquid mixture by pouring it through some filter paper. Then all of your solid would stay up in the filter paper and all of the liquid portion would come down into this beaker. Okay, that can happen with mixtures. It can't happen with pure substances. And within our mixtures, we're going to have two different categories. One category is homogeneous, the other is heterogeneous. Homogeneous or homogeneous, doesn't matter how you say it. When we have a homogeneous mixture, the composition of that mixture is going to be uniform throughout, and the different parts of the mixture are not going to be visible to you. So when you're looking at it, it's going to just look like one thing. Like if you have like a tablespoon of salt and you mix it with a glass of water, all that salt seems like it disappears into the water and it just looks like water when you're done. But what's mixed into the water is now two different things. So salt and the water. That's an example of a homogeneous mixture. Brass is another example of a homogeneous mixture. In this case, it's a solid homogeneous mixture, but the brass is actually made up of copper and zinc atoms that have blended together to make this alloy, okay, which is a homogeneous solid solution or solid mixture. Other types of homogeneous mixtures are gas mixtures. Anytime that you have a mixture of gases, those gases will always be homogeneous. You cannot have a mixture of gases that's heterogeneous. So these are some examples of mixtures that are made of gases for when you're like scuba diving or doing any kind of diving, and you need to have that supplemental air supply. So your breathing mixtures when you're diving can be made up of two gases like nitrox or heliox, where you have nitrogen and oxygen mixed together, or helium and oxygen mixed together. You can also have a trimix of gases where you have oxygen, helium, and nitrogen mixed together. But in all of these cases, you have these different gases in a tank together with each other, but they're not chemically bonded together. They just exist together in that tank, but they still retain their own individual identities. Okay. And if you're looking at nitrox, for example, you could make a nitrox mixture that's 50% oxygen, 50% nitrogen. Or you could make a nitrox mixture that's 60% nitrogen and 40% oxygen. But the amount of oxygen versus nitrogen can be different in each tank that you make up. And that's the definition of a mixture versus a pure substance. The other category for our mixtures is the heterogeneous mixtures. And in our heterogeneous mixtures, the composition of the components that make up our mixture are going to be visibly different from one another. So when you look into a heterogeneous mixture, you'll be able to see the different parts of that mixture. So an example would be if you had like copper metal and water mixed together, you'd clearly be able to see the water versus the copper here. That's an example of a heterogeneous mixture. If you think about like a bowl of cereal and milk, that's a heterogeneous mixture, right? You could see the milk, you could see the cereal. So again, we're going to take a second now. I'm going to stop sharing real quick to talk through this flow chart one more time, because I really do think it's important if you can go through this flow chart, create it for yourself, and remember what questions that you ask for each section. That's going to be really helpful when you're trying to make this determination. So you start off with your matter, and the question that you're going to ask for that first step when you're trying to determine pure substance versus a mixture you're going to ask, does this have, does your sample, whatever you're looking at, does the sample have a fixed composition? Or can it change from sample to sample? Okay, or can the composition change? And depending on your answer to this question, that tells you whether you have a pure substance or a mixture. Okay. If the composition never changes, then you have a pure substance. If the composition can change, then you have a mixture. Okay. So these are the two possible answers that you can give. Now, on the pure substance side, the next question you're going to ask yourself is, does my sample have one type of atom or more than one element? Okay. So then the two answers to this question are going to be there's only one type of atom, which means that there's only one element present, or there's going to be more than one element present. Okay. If there's only one type of atom or one element present, then your sample is an element. If you have more than one element present, then your sample is a compound. All right. And some examples, like we saw some of the examples that they listed out, a lot of the solids, your solid metals on your periodic table are examples of elements. Other examples of elements are things that you might not think of because they're made up of more than one atom, but it's the same type of atom. So things like hydrogen gas or oxygen gas, when you see the H and then the little two there, that means that there's two atoms of hydrogen. Okay. So it's two atoms, but only one type of atom. Okay. So that still makes it an element. And then, of course, like what we saw previously, like aluminum, copper, sodium. Okay. All of those are types of elements. Compounds are going to be things that have more than one type of element. So we looked at like water, for example, carbon dioxide, CO2, nitrogen dioxide, right? So in all of these examples, we have more than one type of element present. But if you look at any sample of carbon dioxide, for instance, regardless of where you get the carbon dioxide from, carbon dioxide will always have one carbon for every two oxygens. Okay, so its composition never changes. So both of these are pure substances still. Okay. On our other side, we've got our mixtures. And the question we're going to ask about our mixtures is it's about the uniformity. Does that make sense? Like the sameness of the composition. We'll ask the question. I'm just going to draw a little line here to separate the two sides. is my mixture uniform throughout? Okay. And if the answer to that question is yes, it's uniform, then your mixture is going to be homogeneous. Okay. If the answer is no, I can see different parts of my mixture, then your mixture is going to be heterogeneous. Okay. And so for some examples here, like all of our gas mixtures, like air, is a homogeneous mixture. I'm just going to put all gas mixtures here because air is not the only one. Things like salt water, sugar water, right? Anything that looks like it's one substance would be a homogeneous mixture. Our alloys, like they mentioned, brass, steel, they're solid, but they still look like just one substance. But it's a mixture of different things that are in there. Um, for our heterogeneous mixtures, again, this is where you would see the different components of it. So, what example did they give us in the slides? Um, oh, they said copper, metal, and water. Yeah, sure. Copper, metal, and water. That's a fine heterogeneous mixture. If you had like sand and water, right? You couldn't dissolve sand in the water, it would just sit there in the water. Cereal and milk. I like that one. All right. So I would say that if you can recreate this flow chart for yourself, then you'd have a really, good resource to be able to answer questions like this when you're looking at your exam. So let's look at some of the questions for the classification. Share my screen again. All right. So it says identify each of the following as a pure substance or a mixture. So pasta and tomato sauce, we have a lot of different components that make these up, but pasta and tomato sauce is not something that is going to exist in um, like in a fixed composition, right? You can make pasta and tomato sauce with a lot of different combinations. So this is going to be a mixture. Draw M there for mixture. And then specifically, if we were trying to figure out if it was homogeneous or heterogeneous, this would be a heterogeneous mixture. I'm going to write with my mouse. So I'm going to write HT for the heterogeneous mixture. Aluminum foil, assuming that it's made from pure aluminum, which you could assume in this case, they weren't trying to tell you that anything else was mixed in. So for aluminum foil, this is going to be considered a pure substance. And if it's a pure substance and it's just aluminum, aluminum is, there's no other type of element present, which would mean that this is going to be an element. Helium is a pure substance. It is also a type of element. And air is going to be a mixture. Air does not have a set fixed composition. It has a common percentage of like nitrogen versus oxygen that you'd find in air that's breathable. But if you go different places, and certainly, like different things can make up the air that you're breathing. So the fact that the components of air can combine differently means that it's not a a pure substance. It is something that's mixed together and it's not forming any kind of chemical bonds between the different gases that make up air. So this is going to be a mixture. Because it's a gas mixture, it's automatically homogeneous. So we'll write HM for that one. Okay, even though it didn't ask us to do the second part, I think it's good practice anyway. All right. Rid of these. All right. Next one. Again, they're asking us for more classification. This time we're doing homogeneous versus heterogeneous for each of these mixtures. And for the mixtures, it's going to be, you're trying to look for uniformity. That's what's going to determine whether something's homogeneous or heterogeneous for a mixture. Okay. So for each of these, you got to ask yourself, if I'm looking at this thing, can I see multiple parts of it? So for a hot fudge sundae, yeah, you could see all the ice cream, the chocolate sauce, whipped cream, the sprinkle, whatever the stuff is that you like to put in your sundaes. All of that stuff you could see separately. So this is going to be a heterogeneous mixture. Shampoo, most shampoo that you would squeeze out of a bottle looks pretty uniform in its gel form. You usually don't see anything that is you don't see like solid chunks or anything like that in shampoo. So this is going to be homogeneous. HM for the homogeneous, HT for the heterogeneous. Sugar water, assuming that you are not trying to dump like an entire bag of sugar into a glass of water. Sugar water should dissolve. Sugar should dissolve completely in a glass of water. So this would be a homogeneous mixture. And then peach pie. There's going to be different parts of the pie, the crust, the filling, the fruit chunks that are still in there. And you'd be able to separate all those out and see them all individually. So this is going to be an example of a heterogeneous mixture. All right. Classify each of the following as a pure substance, and then element or compound, or a mixture, homogeneous or heterogeneous. So again, copper and wire. We're looking at copper wire here. Copper is a pure substance, and copper specifically is an element, lowercase e for element. Um, sorry, my mouse writing is not great. Chocolate chip cookie. Chocolate chip cookie has a variable composition. It changes from, chef to chef. So this is going to be a mixture, and you could see the different parts of the chocolate chip cookie. The dough from the chocolate pieces and whatever. So this is going to be a heterogeneous mixture. And then we have nitrox, a combination of oxygen and nitrogen to fill scuba tanks. Again, when we're combining different gases together, this is a mixture of gases. It's not a chemical reaction. So we have a mixture here. And because it is a mixture involving gases, it is going to be a homogeneous mixture. All right, let's look at the next way that we can classify matter is based on its physical state. The three physical states that we're going to focus on will be solids, liquids, and gases. We want to know what the typical properties are for each type of physical state, how we should describe them. So first is going to be our solids. Our solids are going to have a definite shape, which means that their shape will not change. They'll have a definite volume, which means that their volume will not change. Solids are going to have particles that are very close together. Okay, so they're going to be touching each other essentially when they're in their atomic or molecular form. If you could zoom in really close, you'd see all the atoms, they'd be touching side by side. And the particles that make up your solids are going to be in a fixed arrangement. That means that they don't move. Okay. Specifically, they don't move past each other, right? All atoms and molecules will vibrate in place. So there is some like internal movement there. But they're not going to be moving past one another in a way that will allow their shape to change. Okay. Sorry. They're still going to be locked in a position. And that's what holds the shape of solids firm. Then we're going to have liquids. Liquids are a little different from solids because of how their particles move. The particles that make up a liquid are still very close together. Okay. Very, very close together. But they can move past one another. They're not locked in a position. And that means that the shape of liquids can change, which you know by, pouring anything into a glass. The liquid takes whatever shape your glass is. But because liquids have particles that are still very close together, their volume is still a definite property. It does not change. Okay. So liquids can take the same shape as their container, but their volume is set. The particles of liquids are very close together, but they are mobile, and those particles do move very slowly. Slowly in comparison, in particular to gases. Gases have particles that move very fast, right? The particles that make up gases are extremely far apart from one another, and they're moving very quickly all the time. So this affects the shape and the volume properties of gases. Gases have an indefinite shape, meaning that they are not locked into any shape at all. They'll take whatever shape their container has. Gases also have an indefinite volume, meaning their volume can change. Because all this empty space that's between your gas particles, if you took a balloon, for example, and you decreased the volume of it, you would just end up compressing your gas sample, meaning you'd squeeze it together a little bit. But you're able to do that with a gas sample because there's so much empty space. So if you squeeze these gas particles together, they would just get closer to each other, but there'd still be room for them all. Okay. So because there's so much empty space between these particles, it means that the volume of gases can change when you change the size of the container that they're in. And gases are always going to have the same shape as their container and the same volume as their container. They'll always spread out or come together depending on the change of the container that they're existing in. So this is a good table that just summarizes those different states of matter and the corresponding characteristics. So this is a good one to look at as a refresher. It might be a good idea for a study technique to recreate this table for yourself, but to leave this whole inside part blank. And then just test yourself on being able to fill in these phrases, right? Because if you can do that, then you have a very good idea of what the properties of the solids, liquids, and gases would be. Okay, so we'll identify each description as a solid, liquid, or gas based on what they give us here. It has a definite volume, but it takes the shape of the container. So a definite volume means it could be a solid or a liquid, but if it takes the shape of the container, that means it cannot be a solid. It has to be a liquid. Its particles are moving rapidly. The only state of matter where that is true is going to be for our gases. Its particles fill the entire volume of a container. If the volume is able to change and the volume is able to fill the entire container, for example, that's a characteristic of gases. Your liquids and your solids both have set volumes that cannot change. I said your liquids and solids, right? Liquids and solids have a set volume that cannot change. Only gases volume can change. Its particles have a fixed arrangement. A fixed arrangement means that they cannot move, and that is a characteristic of solids. Its particles are close together, but they move randomly. And that's going to be a characteristic of liquids. Erase, erase, erase. All right, now we're going to look at physical properties versus chemical properties, and physical changes versus chemical changes. Physical properties in general are something that we can associate with a particular substance. It's a characteristic of that substance. Okay, so when we're looking at properties, if we're saying that something's a physical property, it's going to be a characteristic that we can observe without any chemical change to that substance. Okay, no chemical change should happen if I'm observing a physical property. So something like the shape of an object, the physical state it's in, whether it's solid, liquid, or gas, its boiling point and freezing point. These are the temperatures where it would boil or the temperature where it would freeze. These are all things that I can observe without any kind of chemical reaction happening. Types of physical properties of something like copper. It's got that red-orange color. It's shiny. It's able to conduct heat and electricity. Just because you're using copper to conduct heat and electricity, that doesn't mean that the copper is undergoing a chemical reaction, right? It just means that it's being exposed to some heat. If you notice that copper is solid at 25 degrees Celsius, that's a physical property. If you melt copper at 1083 degrees Celsius, that means that your copper goes from solid to liquid. Its physical state has changed, but it's still copper. So chemically, it's still the same thing. So melting, the process of melting something is not a physical change. It's not a chemical change. It is a physical change, which means that the melting point, which is the temperature something melts at, would be a physical property. Because when you're changing a physical state, you're not changing the chemistry of that substance. You're only changing the physical state that it's existing in. And that's going to be a physical change. Same thing with boiling point. The boiling point describes the temperature where your substance has the same vapor pressure as the external surroundings. But we know it as, we get our liquid hot enough, or we get our substance hot enough that it goes from liquid to a gas, right? So we're changing the physical state. It starts off as liquid, it ends as a gas. Those are two different physical states. You still have the same substance, though. Just because it turns into a gas doesn't mean that it's changed into a different element or a different compound. Okay? So the boiling point, which is the temperature that our physical change happens at, would be a physical property. All right? Like we've kind of been alluding to, these physical changes, these are going to be occurring when things happen to our substance that do not involve an identity change. Okay. We should not have a change in the composition. We should not have a change in the chemical formula. The chemical formula of what we start with should be exactly what we end with. Okay. That's the definition of a physical change. We could have a change in the state. We could have a change in the shape. That's fine. but no change in the chemistry. So if we look at these different descriptions of what's going on here, they're asking, is each one a change in the state or a change in the shape? This is just asking you to identify if you're looking at a change from like solid to liquid, liquid to gas, something like that. That would be considered a change of state. Or if you're just changing the physical shape of something. Um, so chopping a log into kindling wood, that's taking a larger piece of wood and chopping it down to smaller pieces. That is going to be a shape change. You're still going to have solid kindling wood, right? It started out as a solid, it ended as a solid. So that's not a state change. It's a shape change. So we'll do SH. Such good handwriting. Water boiling in a pot. So for each of these, ask yourself, like, how does it start and how does it end? And if the physical states match, then it's a shape change. But if they're different, then it's a state change. If water boils, it starts as a liquid and it ends as a gas. So that is going to be a change of physical state. Ice cream melting. You start out with ice cream, and the ice cream is technically kind of solid-ish. It's that, that soft solid that ice cream is sometimes. But as it melts, it turns more liquidy, right? So that's going to be a change in state. Ice forming in the freezer. When you have ice forming, you start out with liquid water and it ends as solid ice. That is going to be a state change. Cutting dough into strips. So you start out with dough, which is kind of solidish, soft solid again. But it doesn't change its consistency at all. It doesn't get more liquidy. And in this case, we're just cutting it from a large piece of dough into strips of a different shape. So this is going to be a shape change. I know that for some of these, when you're thinking about like ice cream melting, you're like, yeah, well, my ice cream melted and it also changed its shape as it melted. If you have a shape change that's happening because the physical state of your substance is also changing, then what you're looking at is a state change. Okay, so like the state change, if the state change causes a shape change, then you have to call it a change of state. But if you are changing the shape, but your state stays the same, then you just have a change of shape. So like think about the chopping wood scenario there, right? You started out with a big solid piece of wood and then you cut it into little pieces that are also solid. That's a shape change. But like with your ice cream melting, you started out with something that was kind of solid. So you put it in a bowl and you left it there and you came back, it's turned completely into a liquid. And that change in physical state is what caused the shape to change. Looking at chemical properties and chemical changes, we're going to focus here on deciding whether or not a new substance has been formed. Okay. When you have a chemical change taking place, your original substance is going to turn into something else. So like you might have some CH4 gas and some oxygen gas, and they combine in a fire and combustion. And on the product side of that reaction, you're going to have the formation of carbon dioxide and H2O. So we start out with two compounds, well, a compound and an element, and then we end with two different compounds. All right, so we're going to see a difference in the starting material and the ending material there. That's what a chemical change is. Any property that can only be observed if a chemical reaction takes place is considered a chemical property. So during a chemical change, a new substance is always going to form. That new substance is going to have a new composition. It's going to have new chemical properties. It's going to have new physical properties. When you expose things to very high temperatures, like when you burn something or when you cook something, when you fry an egg, some like things like that, when you expose things to extremely high temperature, that causes a chemical reaction to occur. So when you have something like um, cooking flan and you have that topping of that caramelized sugar, that the sugar being caramelized by that high heat, that is an example of a chemical change. If you look at the original sugar composition to the caramelized sugar, different chemical formula. So these are just some examples of differences, different types of chemical and physical changes. Notice that for the physical changes, you have things like water boiling. So that's a phase change. You have copper, which is solid, and it's being drawn into thin copper wires. That means that you're changing the shape of the copper. You're taking it from maybe like a flat sheet, and now you're pulling it into wire shapes, but it's still just copper. Sugar dissolving in water to form a solution. You start with solid sugar and liquid water, and when you mix it together, the sugar and the water aren't like forming bonds. You just have sugar that's mixed around in the water, but they're still separate substances. Paper cut into tiny pieces of confetti. It's smaller, but it's still paper. Those are all examples of physical changes. For our chemical changes, we have things like shiny silver metal reacting with air that gives a black grainy coating. This is called tarnishing. Silver tarnishes because it chemically reacts with the oxygen and air. And that coating is the result of a chemical reaction. When you have a piece of wood that's burning, it's going to produce heat, ash, carbon dioxide, and water vapor. Anytime that you burn something or you heat something to a high degree, you're causing a chemical reaction. So at the end of both of these processes, you're going to have products forming that have different chemical composition than what you started with. Iron, when it combines with oxygen, forms orange-red rust. This is another chemical reaction. You have iron chemically combining with oxygen, and it's forming an iron oxide, which is a new compound that is different from iron and oxygen separately. And then if we, notice that earlier, this table here, these are examples of physical changes versus chemical changes. And now we can look at those and apply them to physical properties versus chemical properties. Our physical properties are going to be characteristics of a substance that we can observe without changing the chemical composition. But chemical properties are going to be characteristics that we can only observe if we're watching these chemical reactions happen. Okay. So let's look at some of these examples. Classify each of the following properties as physical or chemical. And we're going to be looking to see if a new substance forms or not. So first example, ice melts in the sun. Whenever we have a state change, that is going to be an example of a physical property, always. Okay. Paper can burn. Whenever something burns, that is going to be a chemical change. You will end up with something chemically different than what you started with. A silver knife can tarnish. The process of tarnishing is that reaction with air to form a new chemical product. That is a chemical change. A magnet removes iron particles from a mixture. So you have a magnet, you stick it into a mixture of iron and other things, and then all of the iron sticks onto the magnet. You have to ask yourself then, does my iron change chemically? Did I do something to turn my iron into something else during this process? And the answer is no. You just removed it from whatever it was mixed together with. So it's still iron at the end of this process, which means that is a physical change. Cutting a pizza, you still have the pizza, it's just in a different shape. So it's a physical change. Iron rusting in an old car. Rusting is always going to be a chemical process because you have a new substance that forms. Okay. Let's erase these. All right, we're going to look at temperature next. Okay, so let's look at temperature. We talked a little bit about temperature earlier when we mentioned what the units for measuring it were. But when you look at the actual definition of temperature, you'll see that it's going to be a measurement of how hot or cold something is. And we usually are looking at this in comparison to another object. You measure the temperature of something using a thermometer. And there are 3 different temperature scales. Okay, the main temperature scales that we use for like everyday purposes are Fahrenheit here in the US, which is kind of a nonsensical scale when you compare it to Celsius, which is the other most common scale. And the whether you're looking at the Fahrenheit scale or the Celsius scale, you're going to see that the whole numbers on the scale are divided up. And the freezing point, we'll say of water as our standard, the freezing point of water and the boiling point of water have certain temperatures associated with each temperature scale. And we're going to see that on the Celsius scale, there's going to be a 100-degree difference between where water freezes and water boils. On the Fahrenheit scale, there's going to be a 180-degree difference between the freezing point and the boiling point. Okay, so let me skip one forward for a minute just so we could look at this. Fahrenheit versus Celsius first. Focus on these two right now. You'll notice that the marks on the Fahrenheit scale are closer together than the marks on the Celsius scale or even on the Kelvin scale. That's because the degree size of the Fahrenheit degree is smaller than the degree size for Celsius. So water freezes at 32 degrees Fahrenheit. Water boils at 212 degrees Fahrenheit. So if you look at the boiling temperature minus the freezing temperature, if you do that subtraction, you'll see that there's 180 degrees Fahrenheit between those two things. If you look at the same two temperatures, but using the Celsius scale, you'll see that water freezes at 0 Celsius and it boils at 100 degrees Celsius. So the difference between boiling and freezing using Celsius scale is 100 degrees. So you see like that's the difference in the size of the degree from Fahrenheit to Celsius. Now the other temperature scale that you should be familiar with is the Kelvin scale. This is going to be think about it like your science scale, okay? This is going to be our SI scale for temperature. It's a very useful way to look at temperature because, very importantly, on the Kelvin scale, there are no negative temperatures, okay? The lowest temperature that exists is represented as 0 on the Kelvin scale. This temperature is also called absolute 0. It is the coldest temperature that exists. There's nothing possible below 0 Kelvin. 0 Kelvin is the same temperature as negative 273 Celsius. Okay, so if you have a temperature of 0 Kelvin, that means your temperature is also negative 273 degrees Celsius. The units for the Kelvin scale is just Kelvin. There's no degree symbol when you're writing out Kelvin temperatures. And what's interesting is that the degree size on the Kelvin scale is the same as the degree size of the Celsius scale. So how do we know that? Because when we're measuring with the Kelvin scale, on the Kelvin scale, remember, water freezes at 0 degrees Celsius. That temperature on the Kelvin scale is 273 Kelvin. Okay. So now when we boil water and we measure the boiling point of water on the Kelvin scale, it's 373 Kelvin. The difference between 373 Kelvin and 273 Kelvin is 100 Kelvin. The difference between where water boils and water freezes on the Celsius scale is 100 degrees Celsius. So because the difference in the units is the same for the Celsius and the Kelvin scale, that's how we know that the size of a Kelvin degree and a Celsius degree is the same. Okay. When we want to convert between temperature scales, we do have a relationship that we can write out between Celsius and Fahrenheit. And that relationship comes from two places. It comes from the degree difference between the size of the degrees between the Celsius and the Fahrenheit scale, right? So we have already written out, right, that there's 180 Fahrenheit degrees for every 100 Celsius degrees. So that means that for every 1.8 degrees Fahrenheit, we'll have 1 degree Celsius. That's how we're going to write out that difference. So in our temperature formula, you'll notice that there's a 1.8 in that temperature formula that connects Celsius and Fahrenheit. This is where the 1.8 comes from. Okay. The other part of our Fahrenheit Celsius formula that you're going to notice is the number 32. And that number 32 comes from the difference between where water freezes for Fahrenheit and where water freezes for Celsius. Okay. So when we write out our temperature formulas, you'll see that to get a temperature represented in Fahrenheit, if we already have the Celsius temperature, we're going to take our Celsius temperature and we're going to multiply it by 1.8 so that we can make the degree size the same as our Fahrenheit degree size. And then we're going to add 32 because Fahrenheit has a freezing point that's 32 degrees higher than Celsius. Okay. So that's how we're going to make those two the same. That's how we're going to adjust one to the other. If we're starting off with a Fahrenheit temperature and we want to change it into a Celsius temperature, then we have to take our Fahrenheit temperature, and the first thing we have to do is subtract 32 so that we're adjusting that freezing point. And then we're going to take that number and divide it by 1.8 so that we make the size of our degrees Celsius sized again. Okay, and so that's how we take our Fahrenheit temperature and we turn it into Celsius temperature. So this is just giving us some examples of different temperatures that represents the same temperature, but it's written in different units. So like water boiling, for example, 212 Fahrenheit or 100 degrees Celsius or 373 Kelvin. Those all mean the same thing. They're just written in different units. All right, so let's look at this example. We'll talk about how to calculate the Kelvin scale from the Celsius scale when that slide comes up, but let's focus here on the converting our Celsius temperature into Fahrenheit. So here it says a person with hypothermia has a body temperature of 34.8 degrees Celsius. And what is that temperature in Fahrenheit? Okay, so when you're asked a question like this, the first thing that you're going to want to do is write out the temperature formula that you want to use to solve the question. In a formula like this one, another thing to keep in mind for significant figures purposes is that numbers that are part of an equation like this, these are going to be considered exact numbers, and these numbers are not going to limit the amount of significant figures that you're going to report. Okay, so in our first step, we're going to do 1.8 times 34.8 plus 32. So we end up with 62.64. I'm writing out all the numbers in my calculator, but I know that I'm focusing on these three. There's three significant figures here. So there's three significant figures here, but I'm just going to write everything down until my last step. And now I'm going to add 32. And I get 94.64. And I'm going to keep my three significant figures here. Okay. All right. The next question says, on a cold winter day, the temperature is negative 15 degrees Fahrenheit. What is that temperature in degrees Celsius? So this time we're going to take negative 15 degrees Fahrenheit and we're going to convert it into degrees Celsius. All right, so for that one, to find our Celsius temperature, we're going to take our temperature in Fahrenheit, subtract 32, that's our first step, and then divide it by 1.8. So we have negative 15 minus 32 over 1.8. So negative 47 over 1.8. And we're going to end up with negative 26 degrees Celsius. Okay. Next question says, what is the normal body temperature? 37 degrees Celsius in Kelvin. Oh, I thought that they didn't tell us. My bad. Before we do that, I guess I'm going to write out the formula. I must have skipped over it in one of the other slides. So let me write out the formula to go from Fahrenheit to Celsius is going to be Celsius equals temperature in Fahrenheit minus 32 divided by 1.8. Go from Celsius to Fahrenheit. It's going to be Fahrenheit equals the Celsius temperature times 1.8 or 1.8 times Celsius. It doesn't matter which way you write that, plus 32. And for Kelvin, you can only relate Kelvin to your Celsius temperature. So if you want to know your temperature in Kelvin, you have to take your Celsius temperature and you have to add 273 to that. Okay. And then conversely, if you want to find your Celsius temperature, but you have a temperature that's in Kelvin, you'll take that Kelvin temperature and you'll subtract 273 from it. If you're given a temperature that's in Fahrenheit and they want you to find it in Kelvin or the reverse, you can't do this directly. There is no direct formula that relates these two things. You have to go through Celsius. So it has to be like this. So you can't do this. Okay. You either have to go Fahrenheit, Celsius, Celsius, Kelvin, or if you're given a temperature in Kelvin, you have to go Kelvin, Celsius, and then Celsius to Fahrenheit. Okay. All right. So let's look at the next question. Says, what is the normal body temperature? 37 degrees Celsius in Kelvin. So if we have a temperature of 37 degrees Celsius and we want to turn it into Kelvin, Kelvin is just going to be that 37 degrees plus 273, which I should be able to do in my head, but here we are, 310 Kelvin. All right, next question says, in a type of cancer treatment called thermotherapy, temperatures as high as 113 degrees Fahrenheit are used to destroy cancer cells or make them more sensitive to radiation. What is that temperature in Celsius and in Kelvin? And so like we were saying, like you can't go from Fahrenheit to Kelvin, anyway. So we'll start by going from Fahrenheit to Celsius. So we'll do our 113 minus 32 divided by 1.8. And we get 45 degrees Celsius. And now to get our temperature in Kelvin, it's going to be our temperature Celsius plus 273. And we're going to get 318 Kelvin for that. All right. The next section talks about energy. So let's look at a few of these slides. For some of our definitions, the definition of energy is the ability for an object to do work. Energy is what's going to make objects move. It's also going to be what fuels things like our chemical and physical changes that happen. There's two main types of energy that we're going to look at, potential and kinetic. Our kinetic energy is going to be considered the energy of motion. Anytime something is moving, it has kinetic energy. So all of these are examples of kinetic energy. Swimming, water flowing over a dam, working out. These all involve movement, so they all involve kinetic energy. Potential energy is energy that's stationary, okay? So think about it like energy that's being stored up to be used later. So things that have potential energy are things that seem to be still because it's saving all of its energy to be used at a later time. Okay. So examples of things with potential energy would be like the water that sits at the top of the dam, but is not flowing over the dam. It's just sitting there at the top. When you have a spring that's coiled up, coiled down and compressed, and it's ready to snap, that has a lot of potential energy. It's not in motion, but it's storing a lot of energy that it's going to be able to transition and translate into motion. Another source of potential energy will be chemical bonds. Anything that has a chemical bond has potential energy in it. Chemical bonds are a great source of potential energy. Okay. And let's talk about what happens before we get there. Let's talk about what happens when energy transitions go on. I'm going to sketch out that really amazing picture from class. I'm sure everyone's thrilled. So imagine that we have use some of my bigger markers here. Imagine that we have a wall, we have the ground, okay, and there's a building up here, okay, and on top of this building is going to be this like a 10-pound weight that's just sitting up there. All right, someone balanced it perfectly, so it's sitting just barely hanging on to that wall. Okay, what we have up here is something that is not moving. It's very still. Okay, this object has potential energy. Okay, and specifically, this object has a lot of potential energy. It has a large amount of potential energy because what we're going to see is that potential energy increases with instability. Oops. Okay, so this weight up here that's balanced on this building like this has a very high amount of potential energy. All right. And it's going to stay as long as it's balanced up there and it's not moving, all of that energy is going to stay as potential energy. Okay. But as soon as something comes around and knocks that weight off of the building, like say that you just walk up and you tap it right there, now it starts falling. All of that potential energy as it falls is going to turn into kinetic energy. Okay. So this whole time when we're in with these red arrows, all of this is kinetic energy. And all of our potential energy converts into kinetic energy. All of our potential energy that we had up here, these high amounts of potential energy, all of that converts into kinetic energy. And there's a reason for that, which we'll talk about in later chapters. But just so this makes more sense, there is a law that works similarly to the law of conservation of mass. It's called the law of conservation of energy. Okay, and this states that energy can't be created or destroyed. Whatever energy we have, that's what we have. If your potential energy, if your object with potential energy starts moving, that potential energy can't just disappear. So it has to turn into something else. And what it turns into is kinetic energy. So energy can't be created or destroyed. It can only change forms. Okay. So now as our weight is falling to the ground, all of that potential energy turned into kinetic energy, but it's only going to stay as kinetic energy until our weight hits the ground. So now once our weight hits the ground, now it's not moving anymore, right? It's stationary again, still. But this time it's still and it's very, very stable. There's nothing for it to fall off of anymore. So it has all the only energy it contains at this point is potential energy again because it's not moving, but it has very low potential energy. Okay, because now it's stable. But all the energy that it fell down with, it still has to go somewhere, right? It can't just disappear. So what ends up happening is that um, whatever whatever of this kinetic energy did not transition into potential energy ends up getting released to the environment as heat or what's called thermal energy. Okay. I mean, these are little heat marks there. So this is going to be our thermal energy. Thermal energy is just another type of kinetic energy, but it's kinetic energy that specifically exists as heat. Right. So we'll put heat in parentheses here. And if you were able to like keep track of the exact amounts of energy present, what you would see is that however much potential energy you started with at the top, if you were able to look at the amount of potential energy at the bottom and the amount of thermal energy that's being released, and you added those energy amounts together, it would be the same amount of energy as what you started with up here. Okay. So let's say you started out with like 100 joules of potential energy. All 100 of those joules of potential energy would convert into kinetic energy. And when your weight hit the bottom, maybe 10 joules of your energy would be potential energy, and like 90 joules would be thermal energy. But when you add them together, you still get that 100 joules that you started with originally. Okay. So that's how our energy is going to work. Um, Now, what you should be able to do is look at different scenarios and decide whether you're looking at potential or kinetic energy based on what the scenario is. So let's take a look at the slides here. Okay, so again, when you're looking at for kinetic energy, you're thinking energy of motion. When you're looking at potential energy, you're thinking energy of that's involved with things that are not moving or things that have, things that are represented as like chemical bonds, substances with chemical bonds. So rollerblading, right? You would definitely be moving while the rollerblading's happening. So this is going to be an example of kinetic energy. A peanut butter and jelly sandwich is not doing anything. It's just sitting there. So this is going to be potential energy. Mowing the lawn, that definitely involves motion. So that's going to be kinetic energy. Gasoline in the gas tank. The gasoline is not undergoing combustion at this point. It's just in the gas tank. So gasoline is a substance that has chemical bonds that have a lot of stored potential energy in them. Okay. So let's look at the relationship between heat, how heat moves and how it sort of moves energy into objects or into substances and out of substances. We're going to see that heat and energy transfers are a big part of the phase changes that we see every day. They're thinking, they're giving the example here of like an ice cube. So when you have an ice cube and you add heat to it, you're supplying the energy that it's going to need for the solid H2O molecules that are stationary to start moving. And once those particles start moving around, now they're not going to, that particles that move are not associated with the solid, right? We talked about that a little bit earlier. When your particles are moving around, that's associated with a liquid. So if you provide enough heat, if you give your solid enough energy, if you give those particles enough energy, they're going to be able to move around enough that they won't be a solid anymore. Now they'll be a liquid. And that's what's going to happen with every state change, every physical state change that occurs. All right. Our energy is going to be measured in terms of joules or kilojoules and calories or kilocalories. The SI unit for energy is the joule, right? So I think we've saw that already. That's a capital J. And kilojoules is just it has your kilo prefix in it, right? So 1 kilojoule is going to be equal to 1,000 joules. When you're looking at the unit of calorie, that's just another way to represent energy. If we put a metric prefix in front of calorie, that gives us a kilocalorie. Oops, and 1 kilocalorie is going to be equal to 1,000 calories. Okay, and the definition of calorie comes from the amount of energy that we would need to raise the temperature of exactly 1 gram of water by 1 degree Celsius. So 1 calorie of energy is enough to raise 1 gram of water by 1 degree Celsius. Okay, that's where the calorie comes from. And if we want to relate the unit of calorie to the unit of joules, this is an equality that relates those two things. So every 1 calorie is equal to 4.184 joules. And that's an exact conversion. Okay. From this equality, we can create 2 conversion factors from that. That's going to allow us to convert between calories and joules or between kilocalories and kilojoules. So we're going to look at a few questions that involve these energy conversions. We'll start here. How many calories are obtained from a pat of butter if it provides 150 joules of energy? And we want to convert that into calories. And our equality for calories is going to be that 1 calorie is 4.184 joules. So if we have 150 joules, then when we set up our conversion factor, we're going to want to use the conversion factor where joules goes on the bottom so that these units can cancel out and calorie goes up top. Okay. And so we'll put our 1 calorie top and we'll put our 4.184 joules on the bottom. Okay, and we get 35.85, which will round to 2 significant figures. So that'll be 36 calories. The next question says a defibrillator gives a high energy shock of 360 joules. What quantity of energy is that in calories? Okay, so we're going to use our same equality here. We're just looking at a different number. So if we have 360 joules, we know that there's going to be 4.184 joules in every 1 calorie. We know we want the joules unit on the bottom again so that it can cancel out with the joules unit that we were given. And we end up with 86 calories. All right. Next questions. Study check 3.5 says, when 1 gram of glucose is metabolized in the body, it produces 3,900 calories. How many joules are produced? So we're going to take 3,900 calories and convert it into joules. So again, we're still using our same conversion here. We're just going to be modifying its position a little bit. So now we're starting out with our 3,900 calories. So now we're going to want the calorie unit to be on the bottom of our conversion factor. And we want our 4.184 joules to be up top so that our calories can cancel out. And we end up with 16,317.6 joules. Our number 3,900 has 2 significant figures in it. So we're going to keep 2 significant figures in our final answer. And we'll turn the rest of those into zeros because we don't have to round. The 3 is below a 5, so we don't have to worry about rounding. So we're going to end up with the final answer of 16,000 joules. And then 3.5 part B says a swimmer expends 855 kilocalories during practice. How many kilojoules did the swimmer expend? If we look back at our conversion here, right? Our conversion is in calories and it's in joules. When you look at kilocalories and kilojoules, remember the connection between those. We said that every 1 kilocalorie is going to be 1,000 joules. And every kilojoule is going to be, every one, let me make sure I to backtrack that. I was looking at the joules and I said the wrong thing. 1 kilocalorie is 1,000 calories, just like 1 joule is 1,000 joules. Okay. So by adding that kilo prefix, we're multiplying both of these things by 1,000. So if I have 1 kilocalorie, which is 1,000 calories, I'm going to just have the same amount of kilojoules as my original conversion. Okay. Because um, writing this out, that's like saying that, remember, 1 kilocalorie is equal to 1,000 calories. So it's like saying 1,000 calories is equal to 4,184 joules, right? The only difference between this and this is that I've divided these numbers by 1,000. Okay. But I can use this to help me answer the question here, um, to write out my conversion. The question again, it says a swimmer expends 855 kilocalories during practice. How many kilojoules did the swimmer expend? And so we can look at this and say, well, every 1 kilocalorie on the bottom so that it can cancel equals 4.184 kilojoules. So 855 times 4.184, 3577.32 kilojoules. We have 3 significant figures here, and so we're going to keep 3 significant figures here. This 7 that follows our last significant digit is going to round our other 7 up to an 8. So our final answer is going to be 3580 kilojoules. All right, let's look at the energy and nutrition next. Share my screen again. So we're going to apply some of this energy stuff, but specifically to some nutrition information. So when you're looking at nutrition labels, you get the calorie information from them. Um, the way that that information is obtained is through something called the calorimeter, which we'll actually see during lab at some point. Calorimeters are these little devices that we can use to measure heat transfer. So how much heat was transferred from an object when it's burned um, into water. Okay. So you'll have a calorimeter that has a measured amount of water in there, and you'll keep track of the temperature of the water during the combustion process. So as the sample is being burned, it's going to be releasing heat, and that heat's going to go into the water, and the water is going to increase in temperature. And so you can figure out how much energy was released based on how hot the water gets. Okay. And that allows us to figure out how much energy is in the food, because whatever energy the water picked up, it came from the food that was being burned. All right. So this is kind of the example of what this looks like. Your calorimeter is like this steel casing. It's going to be surrounded by water. You've got a thermometer here that measures the temperature of the water. You've got some kind of stirring mechanism to like just keep the water moving and keep the temperature, trying to like distribute all the water evenly so that you're not getting like a buildup of temperature in one area, a buildup of heat, which is reflected in the temperature. And then in your chamber itself, this is where you'll have your sample and you'll combust it. This process is going to produce the heat that gets transferred out into the water. And that information gets calculated into calorie values that are put on nutrition labels. What's interesting about nutrition labels is that no nutrition label is written with the units of lowercase calories. Okay. All nutrition labels represent the kilocalorie. And The kilocalorie, another way to write the kilocalorie is with a capital C. So the calorie with a capital C, that is equal to a kilocalorie. Now, this being said, on our nutrition labels, what we will see are kilocalories. Okay, we'll always see, if you ever look at a nutrition label, you'll see that you'll always have a capital C with those calories. Okay, you never see lowercase c's with calories. In other countries, they don't use the calories. They'll show the energy values in terms of kilojoules because that's the standard unit. But what we need to recognize, and it's very important to recognize the difference, when you see a capital C, that means kilocalorie. Okay, and food calories are kilocalories. Food calories are never lowercase calories. This is an example of the standard energy values for 3 different food types. Our main, food, they're not food group, but food classifications: carbohydrates, fats, and proteins. What this little table tells us is exactly how many kilocalories we would expect to get for each gram of this material. So what this column on the table tells us is that when you are ingesting a carbohydrate, you're getting 4 kilocalories of energy for every gram of carbohydrate that you ingest. For fats, you're getting 9 kilocalories of energy for every gram you ingest. For a table like this one where you have units, kilocalories per gram, remember that you can write this out as an equality as well. Okay, so we'll look at that in a second. This table also has the units in terms of kilojoules, which is, the more standard way to write it. But you'd read it the same way. There's going to be 17 kilojoules of energy for every 1 gram of carbohydrate. There's going to be 38 kilojoules of energy for every 1 gram of fat. And there's going to be 17 kilojoules of energy for every 1 gram of protein. What that allows us to do is to calculate the energy amounts of different foods if we know their carbohydrate, fat, and protein breakdown. All right. So we're going to look at this question. We have a cup of whole milk. It contains 13 grams of carbohydrate, 9 grams of fat, 9 grams of protein. How many kilocalories does a cup of whole milk contain? And we'll round our final answer to the tens place. So I would say that for each of these, we'll do the calculations. We'll round each to the tens place, and then we'll add them up. Okay, so let's look at how we go through this process. First, let's rewrite our table, our food table. You don't have to have the food table memorized, but you have to know how to use it. It would be reasonable on an exam to either give you a question with the table in it or to give you the values from the table and ask you to use them. All right, so in our cup of whole milk, we have 13 grams of carbohydrates. We have 9 grams of fats. And we have 9 grams of protein. Okay. Now, to calculate how much energy each of these components is going to contribute, I need to look at this question asks specifically for kilocalories. So I'm going to look at this column. And for each of these, I can write out an equality for each one. Okay. For my carbohydrates, what my table is telling me is that there's 4 kilocalories for every 1 gram of carbohydrate. Right? That's what the information from the table means. For my fats, there's 9 kilocalories for every 1 gram of fat. And for my proteins, again, where there's 4 kilocalories for every 1 gram of protein. All right. With those equalities, now I can say, all right, well, I have 13 grams of carbohydrates. So if every 1 gram of carbohydrate has 4 kilocalories, I can multiply 13 times 4 to figure out how many kilocalories are in my cup of milk from the carbohydrates. Okay. This is the kilocalories from that cup of milk. And we can round this to 50 kilocalories because they told us to round it to the tens place, which is this place. Then we have 9 grams of fat. So now we're going to say, all right, well, I know that for every 1 gram of fat, there's going to be 9 kilocalories. Notice that in our calculations here, like our grams of carbohydrate, it was on opposite sides of the fraction, so it canceled out. Grams of fat is on opposite sides of the fraction, so it cancels out. 9 times 9 is 81. And so we'll round that to the tens place again, so that'll be 80. And then we have 9 grams of protein. Every 1 gram of protein has 4 kilocalories. So that's going to be 36 kilocalories. And we're going to round it to the tens place again. So we'll have to round that 3 up to a 4. And then to figure out how many kilocalories a cup of milk has altogether, we add all these things up. So now we're going to take these values. 50 plus 80 is 130, plus 40 is 170 kilocalories total in a cup of milk, of whole milk. Okay. Let's look at the next example. It's sample problem 3.6, and it's just a different nutrition label. While working on his diet log, Charles observed that the nutrition facts label for snack crackers states that 1 serving contains 19 grams of carbohydrates, 4 grams of fat, and 2 grams of protein. If Charles eats 1 serving of the snack crackers, what is the energy in kilocalories from each type, and what's the total kilocalories? Round off the kilocalories for each food type to the tens place. Okay, so we're going to go through the same process now. We go to our carbohydrates and we say, okay, from our table, we know that there's going to be 4 kilocalories for every 1 gram of carbohydrates. For our fats, we know that there's going to be 9 kilocalories for every 1 gram of fat. And again, look the positioning, right? We have the similar units are on opposite sides of the fraction. And for our proteins, every 1 gram of protein is going to have 4 kilocalories. Okay, so 19 times 4, that's going to give us 76 kilocalories, which will round up to 80. 9 times 4 is going to be 36 kilocalories, which will round up to 40. And again, because they told us to use that tens place. And then here, 2 times 4 is going to be 8 kilocalories, which will round up to 10, so that we're in the tens place. And then to get our total amount of calories in one serving, add all that together. So 80 plus 40 is 120, plus 10, 130 kilocalories. All right. So that's how we can relate our energy to our nutrition labels. Let's look at other ways to calculate heat, heat transfer in general. There is a property of substances called specific heat that is, it's intrinsic to substances, meaning it's a part of them. Okay, so like a substance like water, all water samples all have the same specific heat. Specific heat's not something that changes from water sample to water sample. Specific heat is directly related to how easy or difficult it's going to be to change the temperature of something. Okay. Something like water has an incredibly high specific heat. So it's very difficult to change the temperature of water. This is why like the oceans stay cold even in the middle of the summer, because it takes a very, very, very long time to heat up water. And the more water there is, the more energy would be required to heat it up. We are going to represent specific heat with a capital SH. So when you see the SH, that means specific heat. Specific heat is going to be different for different substances, but specific heat will be the same for that substance, even if you're looking at different samples of the same substance. The definition of specific heat is going to be the amount of heat that's required to raise the temperature of exactly 1 gram of that material by exactly 1 degrees Celsius. Okay. So there's 2 different units that you can use for specific heat. The more traditional unit is the joules over grams degrees Celsius. This is the SI unit. You can also use calories over grams degrees Celsius, though, if you're using the calorie values. And we've looked at the specific heat formula before, actually, when we were solving for our variables back in chapter 1, we used the heat equation and we solved it for specific heat. So we've actually already solved this equation out before. What you're going to see is that the units for specific heat, they're going to mimic the variables that are in the numerator and the denominator positions of your equation here. So heat is in the numerator position. And so the unit that will be in the numerator position for specific heat will either be calories or joules, because these are our heat units, our energy units. Heat and energy, they get used kind of interchangeably because heat's just a type of energy. In the denominator position, we're going to have our grams, which is our mass unit, and our delta T, our temperature change unit, excuse me, in Celsius. So the units that are on the bottom of the fraction bar are going to be grams and degrees Celsius. Now, we already mentioned a few slides ago that it takes exactly 1 calorie to change 1 gram of water by 1 degree Celsius. So we can represent this as, we can use this to represent the specific heat for water. 1 calorie per gram degree Celsius. We also know that every 1 calorie is equal to 4.184 joules. So another way that we can write the specific heat of water is we can say that it's equal to 4.184 joules over grams degrees Celsius. Okay. Both of these values are correct ways to write your specific heat for water. You would use one versus the other depending on whether calories are given or asked for in the question, or whether joules are given or are given or asked for in the question. Okay, but both of these are correct ways to represent the specific heat for water. These are specific heat values for some other substances. So you'll see that every other substance has specific heat values that are significantly smaller than water's specific heat. All these metals over here, none of them even break 1. Water's is 4.184. Over here, some of your like ammonia and ethanol, those get up into the 2s. Water is still 4.184. You'll also notice that the physical state of water changes its specific heat, which is interesting. So when you have solid water, which is ice, ice has a specific heat of 2.03 joules over grams degrees Celsius. Water vapor or steam also has a different specific heat than either of these two things. So you'll see that in a list like this one, the substance name and formula is written down, but also its physical state, because the physical state has an effect on the specific heat. So when you look at these two questions, let's think about the specific heat and think about what we would expect to happen. When the ocean water cools down, what happens to the air that surrounds it? Okay. If the temperature of your water is getting cooler, then that heat has to be going somewhere, right? So as your water decreases in temperature, that means that it's going to be releasing heat into your surroundings. So the air around it would warm up a little bit. For the second question, it says sand in the desert is hot in the day and cool at night. So sand must have a blank specific heat. It wants to know if sand is able to change its temperature drastically, does that mean the specific heat of sand is high or low? Okay. And what we said before, like when you're thinking about water and water's very high specific heat, the fact that water has a high specific heat means that it's very difficult to change water's temperature. That's true for any substance that has a high specific heat. If it has a high specific heat, it takes a lot of energy to change the temperature. So if something like sand changes its temperature very dramatically in a short period of time, that must mean that the specific heat of sand is very low, and it's much easier to change its temperature. Sorry, I lost that word for a second. So let's just underline our answers here. Okay. All right. Now the equation that we've looked at before, but we didn't know what it meant earlier, the equation where our specific heat sort of comes from is called the heat equation. Okay. The heat equation allows us to look at the temperature change that a substance is undergoing and figure out how much heat that temperature change costs. Okay. So our heat equation is written out like this. Heat equals the mass of the substance times the temperature change that happened to it times that substance's specific heat. All right, that's what your heat equation is. And we're going to shorten that up into some symbols. It's going to be heat equals M times delta T. That triangle is the delta symbol, and delta means the change that happens, times capital SH, which is specific heat. Okay, so this is the format that you'll typically see the heat equation written in. But these words, this is what the equation means. Now there's two ways to write the heat equation in terms of units, depending on whether you're working with calories or joules. Okay, if heat is in calories, then you'll still have your mass in grams, you'll still have your temperature in Celsius, but your specific heat will be in calories over joules, or I'm sorry, calories over grams degrees Celsius. If you're working with heat that's in joules, then your mass will still be in grams, your temperature will still be in Celsius, but your specific heat will be in joules. Okay. So the heat unit and the specific heat unit have to match each other. So we are going to look at a few examples here. The first example, it says, what is the specific heat? So we're going to be finding the specific heat. And they're giving us some information. They're telling us that we have 24.8 grams of a metal, and the metal absorbs 275 joules of energy. And the temperature rises from 20.2 degrees Celsius to 24.5 degrees Celsius. Okay. So first of all, let me just fish around for another marker. This one's getting a little rough. Let's write out our specific heat equation again. So, nope, let's write out our heat equation first. So heat equals M for mass times delta T for temperature change times specific heat. Okay. So in the information that they gave us, this is our mass. That's our M value. When they told us that it absorbs 275 joules of energy, this is our heat. They gave us the heat. And here they've given us the temperature change. This delta T value, whenever you see a delta in front of a symbol, what that means is that you're going to take the final temperature in this case minus the initial temperature. Okay, delta always means final minus initial. So our final temperature in this case was 24.5. Our initial temperature is 20.2. Okay, so the only piece of information we don't know here is our specific heat. So we can solve this equation for specific heat by dividing both sides by mass and delta T. And when we do that and we rewrite it, we end up with heat over mass times delta T equals specific heat. Okay. And if you don't remember how to solve that out, you can go back to the chapter 1 video where we did work through that. Now we're going to plug in the values that we were given in the question. So our heat value is going to be our 275 joules. Our mass value is going to be 24.8 grams. And our delta T is going to be our 24.5 degrees Celsius minus 20.2 degrees Celsius. Okay. And that's going to be equal to our specific heat. So we could put this all in our calculator, but I'm going to break it down in one more step. Just because I think it's easier to keep track of our significant figures if we do this subtraction. Okay, so now we have 275 divided by 24.8 divided by 4.3. And we end up with, wait, let me just set them one more time. 2.579. And the units here, or that's a 7. The units here, they stay exactly as they are in the calculation. You have joules on top, and then a fraction bar, and then grams and degrees Celsius down here. Okay. But we're going to round this to 2 significant figures because the 4.3 has 2 significant figures. The other 2 numbers have 3 significant figures. So we're going to keep these 2, and we'll round that to 2.6 joules over grams degrees Celsius. Okay, so the next question here. Well, there's 2 questions on the next slide, A and B. We have dental implants use titanium because it's strong, non-toxic, and can fuse to bone. How many calories are needed to raise the temperature of 16 grams of titanium from 36 degrees Celsius to 41.3 degrees Celsius? So in this case, they're not asking us to find the specific heat. They're asking us to find the energy that's needed, the heat that's needed. So they're telling us that we have 16 grams of titanium, which is our mass value. They're telling us that the temperature goes from 36 degrees Celsius to 41.3 degrees Celsius. So this is going to be our delta T. They don't tell us the specific heat, but in this case, you see the list of specific heats for the metals that's given in the tables there. So it's pretty easy for us to look at the titanium. And in terms of choosing which specific heat value that we should use, the question's asking us for the heat value in calories. So in this case, I would look at my table and I would write down my specific heat value for titanium in terms of calories instead of joules. And with that information, then I'm going to be able to use my heat equation and find the heat value. So 16 grams times delta T, which is going to be 41.3 degrees Celsius, which is my final temperature, minus 36 degrees Celsius, which is my initial temperature, times the specific heat, which is 0.125 calories over grams degrees Celsius. Okay, so our heat in this case is going to be 10.6 calories, which will round to 2 significant figures between our mass and our temperature change. This ends up being like 5.3, which is only 2 significant figures. So we'll round that to 11 calories. Okay, and for example B, says some cooking pans have a layer of copper on the bottom. How many kilojoules? So now they're asking us for kilojoules. How many kilojoules are needed to raise the temperature of 125 grams of copper from 22 degrees Celsius to 325 degrees Celsius. Okay. And so again, this is our mass. This is our delta T, our temperature change. What they're asking us to find is our heat. And we have to look at our table. We have to find copper. And we have to figure out, we have to look up for ourselves what the specific heat of copper is going to be. And in this case, we're going to use the joule value because they want the answer in kilojoules. So for copper, our specific heat is going to be 0.385 joules over grams degrees Celsius. And with that information, now we can write out our heat equation. Okay, so our mass is going to be 125 grams. Our temperature change is going to be 325 degrees Celsius, which is our final temperature, minus 22 degrees Celsius, which is our initial temperature, times our specific heat value in joules. Okay. Also look what happens. I didn't do this cross out before, but watch what happens with the units here. Even in our first example, you see how we had 16 grams? We had the grams unit here. That grams unit cancels out with the grams unit in our specific heat. These Celsius cancels out with the Celsius in our specific heat. And that's why we end up with the unit of calories, because calories is the only one that's left not crossed out. Same thing is going to happen down here. Our grams here is going to cancel out with our grams in our specific heat. Our Celsius from our temperature change is going to cancel out with our Celsius from our specific heat. And when we finish this multiplication, we're going to have a number that's in joules. Okay, so we do 325. I like to do the temperature subtraction first. So that's going to be 303 degrees Celsius times 125 times 0.385. And we end up with a heat value of 14,582 joules. Which, remember to read the question, because an annoying mistake to make for questions like this is doing all this work correctly and then picking the wrong answer because it's not what the question asked for. Okay. This question asks for how much heat is there in terms of kilojoules. So you want to take this number and you want to make sure that you write down that there's 1,000 joules in every kilojoule. So what you're looking at here is 14.6 kilojoules of heat. Okay, we're keeping three significant figures here, so that 8 is going to end up rounding that 5 up to a 6. This would be the right answer. Okay. All right. Let's look at the state changes next. Just verifying that this, yeah, the state changes part of it, the section 3.7, this is the last part of the chapter. But I feel like it was the part that was maybe the most confusing. There was just a lot of information that was happening in here. So we'll try to talk through everything so that hopefully it makes sense. All right, sharing my screen. So when we talk about a change of state, we're talking about the change of the physical state that something is in. So like solid to liquid, liquid to gas, all of those things are state changes. we're going to look at the energy that's either released or absorbed during these processes. Okay. Okay, so we can look at each set of phase changes in pairs. And what we're going to see is that every transition between two physical states has one direction where it's absorbing heat and another direction where it's losing heat. Okay. So, like when we're going from the solid state to the liquid state, to go from the solid to a liquid state, a solid has to absorb heat, which is why there's a plus sign there. And as it absorbs heat, it's going to melt and turn into a liquid. On the other side of that, if you have a liquid and it's going to turn into a solid, then it's undergoing the process of freezing. And for a liquid to freeze, the liquid has to lose heat, which is why there's a minus sign. And as it loses heat, it's going to become a solid. Okay. The temperature where melting happens or where freezing happens is the same temperature. This is called the melting point or the freezing point. What determines whether melting happens or freezing happens is whether heat is being added or heat is being removed. So at 0 degrees Celsius, if you're adding heat, you're going to be turning the solid into a liquid. But at 0 degrees Celsius, if you're talking about water, that is, at 0 degrees Celsius, which is the freezing and melting point of water, if you're still removing heat, then that liquid water is going to turn into solid ice as it freezes. Okay. Melting and freezing are reversible processes, like all phase changes. Every phase change is a reversible process. You just reverse it by either adding or removing heat from the physical state that you're currently in. Okay. Fusion is another word for melting. It's like the fancier word for melting. And the heat of fusion describes, if I go back one slide, it describes the amount of heat that's needed for this change to happen, right? I just told you that if you have a solid and you add some heat to it, it turns into a liquid. Well, the amount of heat that you need for the solid to turn into the liquid, that amount of heat is called the heat of fusion. Okay. So it's going to be the amount of heat that's needed to melt 1 gram of solid into a liquid at the melting point. Or we could think about it as the amount of heat that's released when 1 gram of liquid freezes at the freezing point. Because the amount of heat that you release when a liquid freezes into a solid, that's numerically the same value as the heat that's absorbed when a solid melts into a liquid. It's just that, let's say that the heat of fusion is 10 kilojoules, okay? That means that a solid has to absorb 10 kilojoules of heat, and then it can turn into a liquid. That also means that that same liquid can lose 10 kilojoules of heat, and then it will turn back into a solid, right? So the heat of fusion describes the amount of heat needed for either process, either melting or freezing. It's just that if that heat is absorbed, then melting is happening. And if that heat is released, then freezing is happening. For water specifically, the heat of fusion is going to be represented in either calories or joules. Either one is fine. But we're going to see that if you have solid water, which is ice, and you add 80 calories of heat, of energy, to 1 gram of that ice, then the ice will melt into liquid water. Okay, so 80 calories is the amount of heat energy that you need to add to 1 gram of ice to turn it into liquid water. That energy amount represented in joules is 334 joules. And just remember, the only difference between 80 calories and 334 joules is that conversion factor that we talked about. Okay. I just want to be clear here. It seems kind of random, but remember that every 1 calorie is 4.184 joules. So if my heat of fusion for water is 80 calories and every 1 calorie is 4.184 joules, then um my heat of fusion in terms of joules is 334.72 joules. Okay. So maybe they could have even rounded that up to 335, but that's where the number comes from. It's not like a random number. This is our heat of fusion for water. In calories. Okay, so this right here is in calories. This is our heat of fusion for water in joules. And each of these represent the amount of heat that's needed for 1 gram of water to melt or freeze. Okay. We can use our heat of fusion value to figure out how much heat other amounts of water require for them to melt or freeze. I'm not always going to have just 1 gram of water. I might have 75 grams of water. But what I know is that for every 1 gram of that water, I'm going to need 80 calories of heat to melt it, or I'm going to need 334 joules to melt it. Okay. So we can turn these heats of fusion into equalities that represent that phase change that's happening. Okay. So we can write out our heats of fusion as equalities. Sorry. Heat of fusion as equalities. And we'll write the two versions. Okay, we can write the calorie version, which says that there's going to be 80 calories for every 1 gram of water that's melted or frozen. Or we can write it in terms of joules, where we'll say that we need 334 joules for every 1 gram of water that's melted or frozen. Okay, but now if we look at the question on the next slide, that question says, how many joules are needed to melt 32 grams of ice at 0 degrees Celsius? How many joules are needed to melt 32 grams of ice at 0 degrees Celsius? So we know that we have the ice. The ice is at 0 degrees Celsius, so it's at the melting point. Because the melting point and the freezing point of substances is the same temperature. But in this case, we know we're trying to melt. So we're going to be adding heat. So I've got 32 grams of ice and I'm trying to find joules. So I'm going to use this version of my heat of fusion that has grams and joules in it. Okay. So I've got 32 grams of ice. And for every 1 gram of the ice, it's going to cost me 334 joules to melt it. So I'm going to need 10, 6, 8, 8 joules. I'm going to need 10,688 joules to melt that ice. I'm going to keep 3 significant figures because this number and this number both have 3 significant figures. I'm going to round that 6 up to a 7. So my final answer here is going to be 10,700 joules are needed to melt 32 grams of ice. Just take away the comma, make it less confusing. Okay. So that's our fusion process, which links our solid phase and our liquid phase. Let's look at another pair of phase changes. This is going to be solid and gas phase linked. Okay. And they're going to be linked through the processes of sublimation and deposition. Sublimation is going to be the process of a solid converting directly into a gas. The name of that process is sublimation, and you have to know these names. Okay. The opposite process is when you have a gas and it turns directly back into a solid. In both of these cases, there is no pause at the liquid phase. Okay. It's direct solid to gas and then gas to solid. When a solid converts directly into a gas, this is another process where heat is absorbed, which is why there's a plus sign there. When our gas turns directly into a solid, heat is going to be released. That's why there's a negative sign there. Sublimation and deposition, like all phase changes, are both reversible processes, meaning you can just add or remove heat to force the other change to occur. When sublimation occurs, the particles on the surface of your solid are going to directly change into a gas. An important thing to know about phase changes also is that as phase changes occur, no change in temperature happens at that moment. All of the heat energy that you're putting into your substance is going into the phase change. So you can be heating up a sample, and as the phase of that sample, the word phase and the word state you can use interchangeably. But as you're changing the physical state of that sample, even though you're adding heat to it, you would not notice a temperature change until the state change has fully completed. At that point, once the state change is finished, then you notice a temperature change again. And then deposition is the opposing process where your gas particles are going to change directly to solids. Sublimation's common when you're using like freeze-dried foods because your water vapor changes to solid on contact with your cold surface, right? You don't want that to happen. Freeze-dried foods have a longer shelf life than regular, like I guess like regular frozen foods because there's no water in them. Okay. That water that freezes when where you're freezing your food, that's what's going to cause freezer burn, which can shorten the shelf life of frozen goods. The last pair of phase changes that we want to look at have to do with evaporation and condensation. When we're looking at the evaporation and condensation, we're looking at the switch from either liquid to gas, or in the reverse, gas back to a liquid. Okay. So evaporation is going to be when our molecules that are on the surface of our liquid, when they get enough energy to like leave the liquid and turn into a gas. Okay. And then condensation is when you have your gas molecules that are like floating above the surface of your liquid and they lose enough energy to fall back and like become a liquid again. Right? It's all just about an energy exchange. Um, Boiling is another way to convert liquid into vapor. Uh, Boiling is a specific point in time, though. It's when all of your molecules of a liquid, it's not just water, but this, we're talking about boiling water in this specific case. But boiling is when you have all of your molecules of a particular liquid acquiring enough energy for them to vaporize. Okay, so you'll know something is boiling because you'll see bubbles forming throughout the liquid because all of the liquid is ready to vaporize. The word vaporize means turn into a vapor, which is a gas. So vaporize means turn into a gas. When something is boiling, only the molecules that are at the surface can actually turn into a gas. But if your liquid is boiling, then as soon as one layer of molecules turns into a gas, the next layer is ready to go. So it very quickly, all of your liquid can convert into the vapor or gas phase. That's a little bit different than evaporation. Wait, let me go back one slide. Then evaporation. Evaporation can happen at temperatures that are below the boiling point. And when you have evaporation, you just have that surface layer of your liquid, the one that's closest to the top, and it's just absorbing energy. And as that surface layer absorbs enough energy, then some of the molecules will vaporize and they'll turn into a gas. And now you'll have new molecules that are on the surface of your liquid, and those won't have enough energy to turn into a gas yet. So now that they have to sit and they have to wait and they have to accumulate energy, and eventually they'll be able to turn into a gas as well. So evaporation will also um, allow the liquid to turn into a gas, but it's going to happen over a much longer period of time than when you have boiling occurring. When boiling is happening, that means that all of your liquid is ready to vaporize. It just has to reach the surface of the liquid. Um, the the amount of energy that the numerical amount of energy that connects the liquid and the gas phase is called the heat of vaporization. And this is going to describe the amount of heat that is required, that needs to be absorbed, I should say, for a liquid to turn into a gas. It can also represent the amount of heat that is released when a gas turns back into a liquid. Okay. And specifically, again, this is in relation to 1 gram of liquid. So, or 1 gram of gas, but 1 gram of the substance. So the heat of vaporization for a liquid is when how much heat you would need for 1 gram of this liquid to convert into its gas state. The heat of vaporization in the other direction would be when you have how much energy you would need for 1 gram of the gas to convert back into the liquid state. Just like every other phase change, the vaporization and condensation are reversible processes. And the numerical value for the heat of vaporization and I guess we can call it the heat of condensation because, like it's the reverse of vaporization. But the amount of energy needed for the vaporization process and the condensation process is the same number, right? So again, if it costs 10 kilojoules of energy for 1 gram of liquid to convert into a gas, that means that 10 kilojoules of energy would be released when 1 gram of gas converts into a liquid. Okay. For water, the heat of vaporization value is 540 calories for every gram of water that's vaporized, or 2,260 joules of water for every gram of water. Sorry, 2,260 joules for every 1 gram of water that's vaporized. This works exactly the same way as heat of fusion. Okay, it's just that the this is the number in terms of calories, and if we multiply it by 4.184, this is the number of joules. And both of these values can be written as equalities, telling us the number of calories required for 1 gram of H2O to go from the liquid state to the gas state or the gas state to the liquid state. Okay. But when water is being vaporized, it's absorbing heat. And when water is condensing, it's releasing heat. Okay. So let's look at this question. I'm going to write out the heat of vaporization first, just as an equality again. I like having that written out for us to look at. Heats of vaporization, again, are not numbers you need to have memorized. If you need the heat of vaporization to answer a question on an exam, it'll be provided to you, but you have to know what to do with it. If I tell you what the heat of vaporization is and you don't know how to work with it to solve a question, it's not going to do you very much good. Okay, so we have the calorie version, which is 540 calories for every 1 gram of H2O. And then we have the joule version, which is 2260 joules for every 1 gram of H2O. And the question that they were asking us is how many kilojoules are released. And notice they say released because we're going to be condensing. So how many kilojoules are released when 50 grams of steam from a volcano condenses at 100 degrees Celsius? Okay. So that's going to be our condensation point. Just like we have a boiling point, we have a condensation point. Just like we have a melting point and a freezing point, right? And it's the same temperature. This point, our boiling point and our condensation point, it's the same temperature. Just in this case, our steam is releasing energy. So it's condensing and, we're going in that direction, the condensation direction. So we've got 50 grams. They want us to figure out a value in kilojoules. So it's probably smarter to use this version of our heat of vaporization. We have 50 grams of steam. We know that every 1 gram is going to release 2,260 joules. And then we want to take this value and we want to turn it into kilojoules. You can do this all in one step. We've talked about this a few times. It's up to you whether you want to do the steps one at a time or whether you want to write out a single line of conversions. But once you have the number in joules, then you have to take the joules and you have to convert it into kilojoules. Okay, so we get 113 kilojoules of heat are going to be released during that condensation process. Okay. All right, let's go back to the slides because we're going to look next at what's called our heating and cooling curves, which all describe the process of taking something that's in one physical state and moving it into another physical state. So this is the representation of water, which is what we see most of the time. when you look at this heating curve, I want you to follow along with the description I'm giving you right now. Okay. So we know that water freezes at 0 degrees Celsius, right? So that means that at every point below 0 degrees Celsius, what you're seeing is solid ice. Okay. Any point, any of these points on this little red line that we have that's below 0 degrees Celsius, this is all H2O that exists as solid ice. Now, as we add heat, when we move from left to right on this um, on this graph, this diagram, we're going to be increasing the amount of heat that we're exposing our water to. Okay. So as we give the water, the H2O, more and more heat, we're going to be increasing its temperature. Right. So as we increase the amount of heat, we're going to be increasing its temperature. And so slowly the temperature of the H2O, the solid H2O, it approaches 0 degrees Celsius. At 0 degrees Celsius, this is the melting point of ice. And so now we're going to continue to increase the heat, but you're going to notice that the temperature doesn't change right now because all of the heat that we're adding at this point is all being funneled into melting our ice. So our temperature can't change while the state change is happening. So all of that heat's going in and all of our ice is melting and it's all turning into liquid water. And right at this point, this is where all of the solid ice has all turned into liquid water. Okay. And we're still adding heat to this. But now we have only liquid water. And so now the temperature of our liquid water is going to continue to increase. And we're going to keep on adding heat. And that temperature is going to keep on increasing. And it's going to increase until our temperature reaches 100 degrees Celsius. And now at this point, our water, our liquid water, is going to start to boil and turn into steam. And during this whole section where we have this flat line here, all of the heat that we're adding, all of it is being used to boil our water. None of that water is increasing in temperature. All of that heat energy is going into changing liquid water into steam. And only at the point where all of our liquid water has turned into steam, only at that point does our temperature of our steam start to increase up above 100 degrees Celsius. And now as we continue to add more heat, now the temperature of our steam just gets higher and higher and higher. Okay. So there's two important sections of this heating curve. It's a heating curve when you add heat, and it's called a cooling curve when you remove heat. So this version of it where we're adding heat is called a heating curve. And in your heating curve, you're going to have these slanted lines, which are slopes. And every time that you see these slanted lines, this is a point where your state change, or I should say where your physical state is not changing. The only thing that's changing during these sections where you have the slanted line is the temperature of your substance. Okay. So this portion from -40 up to 0, this is a temperature change, but our physical state is a solid that whole time. The only time when I have a state change happen is when I'm at these flat portions of my heating curve. These flat portions, which are called plateaus, this is when I do not have a temperature change because all of the heat energy that I'm adding is being directed into changing the physical state of my substance. And then again, I have the slanted line here. So this is my temperature change where I'm increasing my temperature from 0 degrees all the way up to 100 degrees. And now once I'm at 100 degrees, I have another plateau. And this is where all of my energy is being directed into changing the liquid water into water vapor, into steam. and my temperature will stay constant. It will stay at 100 degrees Celsius until all of the liquid water has turned into steam. At that point, then my temperature can start to change again. Okay. So you'll have plateaus and sloped lines, your slanted lines on your heating curve. And your plateaus are going to represent changes in your physical state. But you will not have a temperature change when you are looking at the plateaus. What you will have is a constant temperature. Okay. And for your sloped lines represent your change in your temperature. Your temperature will not be constant during these periods, and you will not have a change of state during those periods. All right. I know the heating and cooling curves are weird to look at, but they really make sense if you can talk yourself through the process that you're looking at. Try to tell yourself like the story of the heating curve, like I just told it to you. I mean, grab someone, grab a friend or a family member and try to tell them. That's probably the easiest way to really understand it, is trying to explain it to someone else. So when you look at in this case, I want us to use the cooling curve for water to answer the following questions. So we'll draw the cooling curve for water and then we'll look at each of these. The cooling curve for water is just the opposite of the heating curve. You can draw it from left to right or you can draw it from right to left. It doesn't really matter. What's going to matter is how you're tracing it along. Like we know that we're going to be looking at it this way. Okay. So now every time that we know that this is water, okay, so draw out our axis here. So in this area, this is when we're going to have our water represented as steam. This area here is going to be our liquid water. And then this area here is going to be our solid, our ice. This point here and here, this flat line for water, this line happens at 100 degrees Celsius. And that's where we have our boiling point, right? The other flat line, that occurs at our freezing point. So both of these points, that's supposed to be a perfectly straight line that connects them. This happens at 0 degrees Celsius. Okay. Condensation is when we have our gas turning into a liquid, right? So this is when we have a gas state. This is when it's at a liquid state. And so the temperature, the first question says water condenses at a temperature of. Well, if this is our gas state and this is our liquid state, the temperature that conversion happens at is 100 degrees Celsius. The second question says, at a temperature of 0 degrees Celsius, what happens to liquid water? At a temperature of 0 degrees Celsius on the cooling curve, that means that we're still removing heat from it. At 0 degrees Celsius, our liquid water is going to turn into a solid. Okay, and that process is called freezing. 40 degrees Celsius is going to be somewhere between these, right? So let's say that this is 40 degrees Celsius. The third question says, at 40 degrees Celsius, water is, and it wants to know the physical state. So at 40 degrees Celsius, our water is going to be liquid. And the final question on that learning check says, when water freezes, heat is, and they want to know if it's added or removed. When water freezes, heat is being removed from the water, which is what allows it to go from its liquid state when the molecules are moving around into its solid state where the molecules are sort of locked into position. All right. Next question. It says calculate the total heat in joules. Oh, let me put it up on the board. I'll put it on the screen real quick just so you can see the question while I write down some of the information. We're trying to find the heat in joules, and we're converting 15 grams of the liquid ethanol at 25 degrees Celsius to its boiling point. So boiling point will be BP of 78 degrees Celsius. They told us that it's liquid at 25 degrees Celsius, and we're going to be bringing it up to its boiling point, and we're going to be vaporizing it. They also tell us that ethanol has a specific heat of 2.46 joules per grams degrees Celsius. And it has a heat of vaporization of 841 joules per gram. Okay. And the question again that they're asking us here is calculate the total heat needed to convert this liquid ethanol to gas. Okay. I mean, obviously they gave us specific amounts, but they want the total heat. And so there's two things happening in this process. There's a temperature change that happens because remember that we have the liquid ethanol at 25 degrees Celsius, right? And that liquid ethanol cannot vaporize until it reaches 78 degrees Celsius. So a temperature change happens first. It goes from 25 degrees Celsius to 78 degrees Celsius. Then at 78 degrees Celsius, a state change happens. This is when our liquid is going to go into the gas state. Okay. And so we need to calculate the heat for each of those steps. And when you're trying to figure out, well, like, how do I do that? We're going to remember that when we have a temperature change that happens, we're always going to use our heat equation to figure out the amount of heat that a temperature change requires. And whenever we're looking at a state change, we're always going to use that same equation, not really an equation, but that same math that we did in a few slides ago, where we use our heat of vaporization, right, to help us figure out how much energy this state change is going to cost us. Okay. So we're going to do each of these steps individually, and then we're going to add them together to figure out what the total value is. So for our first part, we're going to use our heat equation. And for our second part, we're going to use heat equals grams times the heat of vaporization. Okay. And then we're going to add those values together. So heat equals mass times delta T times specific heat. We have all of that information. They gave us all that information. The mass is 15 grams. Our temperature change is going to be our final temperature of 78 degrees Celsius minus our initial temperature of 25 degrees Celsius. And our specific heat of ethanol, they gave that to us right here. Okay. So this is the amount of energy that was needed just for the temperature change. And now we need to know how much energy it costs for us to do the state change from liquid to gas. So to do that, we're going to take our grams of ethanol times the heat of vaporization of ethanol. So that's going to be our 15 grams again. And remember what we said about heat of vaporization, that we can write this out as an equality. So we can write this out as 841 joules for every 1 gram of ethanol. All right. And when we write it out like that, it might be a little bit easier then to see what our next step has to be, because we can set up that little conversion factor, right? Our 1 gram of ethanol is going to go on the bottom so that our gram units cancel out. And our 841 joules goes up top. And we get 12,615 joules. And this is the energy that's needed for the state change. Okay. And then our total energy is going to be to take these two numbers and add them together. All right. So our total energy required is going to be 1955.7 joules plus 12,615 joules. And we end up with 14,571 joules, which we're going to have to cut down to 2 significant figures based on the 25 degrees Celsius. That's going to end up limiting us. So we can round this to 15,000 joules. Let me just push that up a little bit. There we go. 15,000 joules. All right. All right, next question. Back to volcanoes. When a volcano erupts, 175 grams of steam at 100 degrees Celsius is released. How many kilojoules are lost when the steam condenses and then freezes at 0 degrees Celsius? So we want to know a kilojoule value. And it's going to be really helpful for you in a question like this one to track what's happening here. So like they're telling us that you've got steam at 100 degrees Celsius. Okay. So fine. So now I've got steam at 100 degrees Celsius. If I'm removing heat from it, okay, if I'm cooling it down, that means that my steam at 100 degrees Celsius, the first thing that it's going to do, it's going to condense and it's going to turn into liquid at 100 degrees Celsius. Right? So the first thing that's going to happen is condensation, which is a state change. The second thing that's going to happen is that my liquid that's at 100 degrees Celsius is going to keep losing heat and it's going to become liquid with a temperature of 0 degrees Celsius. So this part here is going to be a temperature change that's happening. But I want to freeze this liquid. So my liquid at 0 degrees Celsius is going to turn into a solid at 0 degrees Celsius. And this transition from liquid to solid, that's freezing, which is another state change. Okay, so I have a state change and then a temperature change and then another state change that's happening. And I have to figure out how much energy each of these changes is going to release. And then once I know how much energy each step releases, then I can add them together to figure out what the total amount of kilojoules released would be. Okay. So for my condensation state change, I am going to need the heat of vaporization of water, right? Because whenever we're doing gas to a liquid or liquid to a gas, we're going to use the heat of vaporization for that. And we're working in terms of kilojoules at the end, so we'll use our joule value. So our heat of vaporization is going to be 2260 joules of heat is going to be equal to 1 gram of H2O. For our temperature change, we're going to need to use heat equals mass times temperature change times the specific heat. This is water, so we'll need the specific heat of water for this. The specific heat of water is 4.184 joules over grams degrees Celsius. And then for our last step there, we're going to be freezing the water. And when we're going between liquid and solid or solid and liquid, we're going to use the heat of fusion for that transition. And our heat of fusion in joules is 334 joules for every 1 gram of H2O. All right. So with that information, we can look at the 175 grams of steam and look at each step. So for our first step here, for our condensation step, if we have 175 grams of steam of H2O, we know that every 1 gram is going to release 2,260 joules of heat. Which is going to be 395500 joules. Right here, you can turn this into kilojoules. Our final answer has to be in kilojoules, so we can just turn all these into kilojoules as we go before we add them together. Or you can wait till the end. Either way is fine. But we're going to end up with like 396 kilojoules from our condensation. Okay. Then we have to do our temperature change. Our temperature change is going to be our heat equation. Heat equals our mass, which is 175 grams, times our temperature change. Our temperature change, our final temperature is 0. Our initial temperature is 100. And then our specific heat for our liquid water is going to be 4.184 joules over grams degrees Celsius. And we end up with negative 73220 joules, which again, we can convert this into kilojoules right away. Which will be negative 73.2 kilojoules. And what this tells us, that negative sign, what that negative sign tells us is that 73.2 kilojoules of heat is released, right? That's what that negative sign means. It means that heat is released. And now we want to look at our final phase change, which is going to be our fusion phase change. So we'll take our 100, just number these, step 1, step 2, step 3. We're going to take our 175 grams of ice, and this time we're going to use our heat of fusion equality to set up our calculation. Every 1 gram of the H2O is going to release 334 joules. Okay, and then we'll take these joules and we'll convert it into kilojoules. 1, 2, 3, 58.5 kilojoules. And now we're going to look at all these heat values. This is what was released in our condensation step. This is what is released during our temperature change. This is what's released during our freezing. To get the total, we have to add them all together now. Okay. So our total heat released is going to be 396 plus 73.2 plus 58.5. And we're going to end up with 528 kilojoules of heat released total. Okay, so next question. In a sauna, 122 grams of water is converted to steam at 100 degrees Celsius. How many kilojoules of heat are needed? So this is, again, vaporization because we're going from grams of water, liquid water, into steam at 100 degrees Celsius. So we're going to need our heat of vaporization value. This is sample problem 3.8. So let's write out our heat of vaporization first. For water, again, heat of vaporization for everything isn't the same. It's just that water is the most common example that they give us. So that's going to be 2260 joules for every 1 gram of H2O. And they're telling us that we have 122 grams of water converting to steam at 100 degrees Celsius. And they want us to find the heat in kilojoules. Really important that you pay attention to this too, because you can calculate the answer, you can calculate the value in joules, and that number might be an answer choice on a multiple choice test. So part of what you need to do is really pay attention to the units so you know that your not just your number matches, but that your number and your unit both make sense together. Okay. Um, so here we're tracking the heat of a phase change. We have 122 grams of H2O. Every 1 gram is going to absorb 2,260 joules. Big number here, 2,75720 joules. So now we have to take this number and we have to turn it into kilojoules. All right, and that's going to give us 276 kilojoules. All right. Next question is study check 3.9. This one says, how many kilojoules are released when 75 grams of steam at 100 degrees Celsius condenses, cools to 0, and then freezes at 0 degrees Celsius. This is very similar to the problem that we did earlier with the volcanoes steam. In this question, the wording is a little bit friendlier though, because they're helping actually trace the process for you, because they're telling you that the steam condenses, cools to 0 degrees Celsius, and then freezes at 0 degrees Celsius. All right. So we're going to need our heats of fusion and vaporization for this one. I'm going to write them up here so we can just have them written down. So heat of fusion is going to be 334 joules for every 1 gram of H2O. And then heat of vaporization is going to be 2260 joules for every 1 gram of H2O. All right, and so again, if you're tracking down what's happening here, we're taking our steam at 100 degrees Celsius and we're turning it into liquid water And then we're going to take our liquid water that's at 100 degrees Celsius and we're going to cool it off so that it's liquid water at 0 degrees Celsius. And then we're going to take our liquid water at 0 degrees Celsius and we're going to freeze it. And it's going to turn into a solid. Okay. So this is going to be our condensation, which is our state change. 100 degrees Celsius to 0 degrees Celsius is our temperature change. And then our liquid at 0 to solid at 0 is another state change. Okay, so remember, for our state changes, we're going to use our heats of fusion and our heats of vaporization. For our temperature change, we're going to use our heat equation. Okay, so step 1 is going to be this first state change. So we're going to take our 75 grams of steam, and we're going to say that in this case, we're condensing it. So we're going between gas and liquid. So gas and liquid means I'm using my heat of vaporization value. So every 1 gram of H2O is going to be 2260 joules of heat. Okay. Step 2 is my temperature change. So to find the heat for the temperature change, it's going to be my mass of 75 grams times my final temperature of 0 minus my initial temperature of 100 times my specific heat for water, which is still the same 4.184 joules over grams degrees Celsius. All right, remember that for our temperature change, that heat equation is mass times temperature change times specific heat. Okay. So 75 times 4.184 times 100. And remember that this negative sign means that heat is being released. So this tells us that, do another equal sign. This tells us that 31380 joules of heat is released. Okay, we didn't turn these into kilojoules yet, but we'll do that before we add everything up. And then our third step is going to be our final state change from liquid to a solid. That is going to be our fusion state change. So 75 grams of steam, every one gram of H2O is going to release 334 joules. Okay, and now that we have the joules for the individual steps, we can convert them into kilojoules. So for each one of these, there's going to be 1,000 joules in every 1 kilojoule. So we're going to have 169.5 kilojoules. We're going to end up rounding this all to 3 significant figures at the end, but we'll just keep everything. You can round before or after. I'm just going to keep it like this for now. Over here, again, 1,000 joules for 1 kilojoule. 3, so this is going to be 31.4. And 5.1 kilojoules. Okay, and now to get my total heat released. It's going to be 169.5 plus 31.4 plus 25.1. And we're going to end up with 226 kilojoules of heat being released. Okay. All right. The last question that's in your packet, it's very similar to this one, but it's the reverse process. So I'm just going to do it for completion, but we've done this like 4 times already, so understandable if you don't want to watch this last one. We'll leave our heats of fusion and our heat of vaporization up there because we're going to need it again. But this final question says, this is going to be in terms of, oh, you know what? They did make it a little bit different. This is going to be in terms of kilocalories instead. So the question says, how many kilocalories are needed to convert 18 grams of ice at 0 degrees Celsius to steam at 100 degrees Celsius. So by using the kilocalories, that makes it at least a little more interesting because we're going to have to use our calorie versions of these values that we've been working with. Okay. Just give me a second to go back and get the calorie versions of these. So for our heat of vaporization, it's 2260 joules for every 1 gram of water, but remember it's 540 calories for every 1 gram of water. And then for our heat of fusion, it's 334 joules, 80 calories for every 1 gram of water that's frozen or melted. And then our specific heat, we'll have to use the calorie version as well. But again, if you think about the pathway that we've been tracing out, you can make that, we can still write that out for ourselves because it helps us organize what we have to do. We're going to take this 18 grams of ice that's at 0 degrees Celsius. And then the first thing we're going to do is turn it into liquid at 0 degrees Celsius. Okay, so this is a phase change or state change. And the state change is going to be fusion. Then we're going to take our liquid that's at 0 degrees Celsius and we're going to raise the temperature of it so that it's liquid at 100 degrees Celsius. This is going to be our temperature change. And for our temperature change, we're going to need our heat equation. Mass times delta T times specific heat. And in this case, because we're working with calories, our specific heat is going to be 1 calorie per gram degree Celsius. That's the specific heat for water when we're using calories instead of joules. Okay. Then we're going to take our liquid at 100 degrees Celsius and we're going to turn it into steam at 100 degrees Celsius. So that is going to be a state change. and the state change is vaporization. Right? So now that we have that all sort of planned out, now we can just do our 3 steps. First, we'll do our state change, our fusion state change. We have our 18 grams of our H2O. And we see that every 1 gram of H2O is going to require 80 calories of heat. So 18 times 80. We want our answer in terms of kilocalories, so we can go ahead and convert that now. There's going to be 1,000 calories in every 1 kilocalorie. And we'll end up with, looks like 2 significant figures here. So 1.4 kilocalories. Our second step, we're going to use our heat equation to track the temperature change. Heat is our mass of 18 grams times our delta T, which is going to be our final temperature of 100 degrees Celsius minus our initial temperature of 0 degrees Celsius, times our specific heat in terms of calories this time. So 1 calorie per gram degree Celsius. I can't believe I just put that in my calculator. So we end up with 1,800 calories. And then we can convert that again into kilocalories because there's 1,000 calories in every 1 kilocalorie. You have 1.8 kilocalories. So that's our first step. That's our second step. And now we'll do our final phase change where we do our vaporization. So our 18 grams of H2O. And for this one, every 1 gram of H2O is going to be 540 calories. Which gives us 9,720 calories. And again, we'll take our calories and convert them into kilocalories. And we get 9.7 kilocalories. And now to find our total heat that was released, we're just going to add all of these steps together. Just verifying that that's, yeah, how many kilocalories are needed. Okay. So our total kilocalories are going to be 1.4 plus 1.8 plus 9.7 . So it's going to be 12.9, which 2 significant figures. So that's going to be 13 kilocalories total. Okay. And that's that for chapter 3.